Hello, I'm Alastair Donaldson. I'm a software engineer at Google and a professor at Imperial College London, and this is joint work with my colleagues Hugues and Paul on putting randomized compiler testing into production. It's an ECOOP experience report paper, and it's about the story of GraphicsFuzz, originally a research project at Imperial College London, that my colleagues and I turned into a startup company of the same name that Google acquired in 2018 and then open sourced. And we've been working at Google on making GraphicsFuzz improve the reliability of shader compilers for the Vulkan programming model. What I'm going to do is give you an overview of what GraphicsFuzz is and how it works, and then tell you about the impact we've been having by using GraphicsFuzz to find bugs in Vulkan shader compilers and use these bugs to grow the Vulkan Conformance Test Suite to provide value for the whole of the graphics community. And then I'll tell you about how we've gone beyond bugs and have used GraphicsFuzz for differential code coverage, being able to grow the Vulkan Conformance Test Suite with new tests that provide further coverage. So what is GraphicsFuzz? Well, it's a metamorphic approach to testing shader compilers that was inspired by work on equivalence modulo inputs testing from PLDI 2014. The idea is a graphics driver is what makes things be rendered on the screen of your device through the graphics processing unit. And a major component of the graphics driver is the shader compiler, which takes a graphics program called a shader and turns that program into machine code to run on the GPU to ultimately render an image. And what we're interested in doing is finding defects in graphics drivers, in particular defects in shader compilers, that either manifest as miscompilations, where the shader compiler generates wrong code, or as crashes, where the shader compiler aborts on compilation or compiles a shader that goes rogue and causes the driver to crash. What we do in GraphicsFuzz is we take some original shader program that renders some image. We don't necessarily know what image, but some image. And from that original shader, we use semantics preserving transformations to derive a whole series of variant shaders. These are shaders that are equivalent to the original shader in that they should render the same image, but they may look very different from the original shader, thus they give the shader compiler a really good workout. Every one of these variant shaders, where we push it through the graphics pipeline, will produce an image, and if all goes well, these images should look identical. They may be slightly different due to floating point precision issues, but they should be very similar to one another. If there's a miscompilation, then we may end up finding that one of the variant shaders gives a significantly different image compared with the original shader. Or we might find that a crash occurs and maybe the shader compiler aborts, or perhaps the device or machine completely fails. The way GraphicsFuzz works is it transforms an original shader into a typically much larger and more complex variant shader. And if we would give this variant shader to a compiler developer and say, look, there's a bug in your compiler, good luck figuring out what's wrong, that wouldn't be very useful. So what we also have with GraphicsFuzz is a reducer. And what that does is it takes the bug triggering shader and it repeatedly tries removing transformations, keeping the smaller shader that results if it preserves either the bad image or the crash. And this ultimately gets down to a very small shader that suffices to trigger the bug. To give you a little example, here's an example of a wrong image compiler bug that we found some time ago. On the left-hand side, you can see the original image that should have been rendered. On the right-hand side, you can see a bad variant image that was rendered, and the difference is really small. There was a return statement, return default color, and this has been replaced with a trivial switch statement that switches on the value 0, and in the case where 0 is indeed 0, it returns default color. So clearly this change should have no semantic impact on what the shader renders, but in fact we got a completely different image being rendered as a result of making this small change on a particular graphics driver. When GraphicsFuzz finds a compiler crash bug, the reducer can actually be much more aggressive and shrink the shader down to the smallest shader that suffices to trigger the bug, with no need to keep it equivalent to the original shader. This is an example of a shrunk down shader that triggered a compiler bug shortly after we arrived at Google. This shader just invokes the pow intrinsic function with a couple of vectors. It doesn't do anything with the result of pow, but just having pow present in the shader in this form was enough for that vendor's shader compiler to crash. When we joined Google, our goal was to make the Vulkan API as reliable as possible with respect to shader compilation, because Vulkan is a relatively new API that is seen as the future of graphics. But a problem we had was that GraphicsFuzz was actually designed to work with OpenGL, which is a very widely used but now somewhat legacy API, and not designed to work with Vulkan. So I'm going to now tell you a bit about how we leveraged GraphicsFuzz to nevertheless test Vulkan shader compilers. GLSL is the shading language associated with OpenGL, the OpenGL shading language, and Vulkan has a different shading language called SpearV. But SpearV is pretty low level, and you wouldn't want to write SpearV code directly. So there is a translation tool called GLSlang that can take a GLSL shader and compile it into a SpearV shader. So this very widely used tool immediately gives us a way to get from the OpenGL world into the Vulkan world. The only thing is that GLSlang is deliberately a simple, non-optimizing compiler, and the SpearV it produces is thus not necessarily all that interesting. But there's another tool called SpearVopt, which is a source-to-source SpearV optimizer that takes some SpearV and turns it into an optimized form, and this allows us to make the SpearV we get from GLSlang a bit more interesting. So what we have been doing is working with GraphicsFuzz in the OpenGL world, taking an original shader and transforming it to a variant, and then pushing both of those shaders through GLSlang to get SpearV versions of them, optionally optimizing the variant shader to make it more interesting still, and then passing these on to the Vulkan driver under test and looking for crashes or image differences. This has been working really well. Clearly, there are parts of the Vulkan programming model we can't hit using this cross-compilation approach because of the idiomatic nature of code that GLSlang generates and that SpearV can produce after optimization. But nevertheless, we can hit a large and important part of the surface area of Vulkan shader compilers. Interestingly, we can also find bugs in GLSlang and SpearVopt themselves, which is great because those are widely used tools in the Vulkan ecosystem. A challenge that we discuss in the ECOOP paper that this presents, though, is if there's a miscompilation bug, we don't know immediately whether it occurred in the Vulkan driver under test or in SpearVopt or in GLSlang. Suppose we found a bug in a Vulkan driver. There's a question of where a report for this bug should go. An obvious thing is to report it to the developer of the driver, but that on its own has limited value. The bug might fall off their radar, and even if they do fix it, the fix might not propagate to end-user devices because driver makers design a shader compiler and driver that gets ultimately given to device manufacturers, but those manufacturers are reluctant to update the driver unless they strictly have to. And if we only give the bug report to the developers of one particular driver, the test associated with the bug doesn't provide value to the rest of the ecosystem. So instead, what we can do, which has higher value, is add a test exposing the bug to the Vulkan Conformance Test Suite. This is a suite of tests that GPU makers run all the time. So if a test lands in that suite that exposes a bug, the GPU makers whose driver this affects will learn about the bug. And furthermore, all devices have got to pass the latest CTS to qualify as being Vulkan conformant. So if a test lands in the CTS, it ensures the bug will eventually be fixed for all future devices. And because the test is available to everyone, it provides value across the ecosystem. Adding a test to CTS requires a bit of care, though. It's really important that the outcome of a Vulkan CTS test doesn't depend on undefined or implementation-defined behavior. If a test does depend on this behavior, then hopefully it will get caught when it's submitted to the CTS, and that will waste code review time, which isn't good. But an even worst case scenario is that an invalid test actually gets accepted into CTS, and only months or years later causes trouble because the fact it depends on undefined or implementation-defined behavior becomes a problem when a shaded compiler changes, and this can be very difficult to rectify after the fact. Some challenging undefined behaviors that we discuss in the ECOOP paper include infinite loops, out-of-bounds accesses, and uninitialized variables. And a big challenge that's very difficult in the graphics domain is floating point precision. And we've got a number of safeguards to ensure that we don't add tests to CTS that are prone to these undefined and implementation-defined behaviors. The GraphicsFuzz CTS workflow we've thus built involves a process of continuously generating a shader, running it against the device, if it triggers an interesting bug, reducing it, then looking to see whether it's similar to other bugs we may have seen before, and if it isn't, converting it into a bug report and making a CTS patch from that bug report so that a corresponding test can be contributed directly to the Vulkan Conformance Test Suite. Regarding bug deduplication, for crash bugs, what we do is automatically analyze the crash report and find the signature of the function at the top stack frame and make from this signature a string that's called the bug signature. And then we bucket crashes by signature and make sure we only add one test to the Vulkan Conformance Test Suite per distinct signature. As well as finding bugs, we've also been using GraphicsFuzz to grow the Vulkan Conformance Test Suite in response to coverage gaps we identify in drivers via differential code coverage. Suppose we've got the driver source code for a particular GPU driver. We can run the whole of the Vulkan Conformance Test Suite against this GPU driver, and we can compile the driver with coverage enabled to measure which bits of the driver get covered by running the Vulkan CTS. We can also run GraphicsFuzz for some period of time and measure which bits of the driver get covered by GraphicsFuzz tests. And if we look at the portion of this Venn diagram of tests only covered by GraphicsFuzz and not by the CTS, this is really interesting. This points to parts of the driver source code that are reachable by Vulkan workloads. So they're not dead code, they're not code that only applies to some other API, but that CTS does not hit. So this is achievable coverage that's missing from CTS. So if we find a piece of code that is coverable by GraphicsFuzz and not by CTS, then there must exist some fuzz shader that hits that piece of code. Suppose we zoom in on that piece of code and find there's a particular statement, like this return statement, that we're able to cover that CTS doesn't cover. What we can do is we can add an assertion before that statement. This is an assertion that makes covering that statement look like finding a bug in the graphics shader compiler. Now, if we run the fuzz shader again, this assertion will fail, and GraphicsFuzz will think it's found a bug, and it can invoke its reducer to try to find the smallest shader possible that triggers that bug. So here, we're really reducing not with respect to a bug, but with respect to a piece of coverage. And this is very similar to the idea of cause reduction from Gross et al. From ISTA 2014. What we end up with is a small shader that triggered that assertion failure. And if we remove the assertion failure, we now have a small shader that covers the line of code that we couldn't cover with the Vulkan CTS. And what we can then do is manually work on this shader a bit to give it a more interesting oracle and submit it as a test to Vulkan CTS to improve the coverage of that test suite. What do I mean by improving the oracle? Well, if you look at this example on the left, this is a tiny shader that we shrunk down that achieved some new coverage on a driver. And what this shader does is just calls the dot product function on a couple of vectors, and it doesn't do anything with the result of that dot product call. So what would it mean to pass this test? Well, the test would just call the dot product function and then do nothing else. So we could at least check that this shader compiles successfully. But instead, if we actually make a condition saying that the dot product of these vectors has to be 0, and if it is 0, we render red, otherwise we render black, and then if we design the test to pass if and only if red gets rendered, then we have a more useful test. We not only have to successfully compile this shader, but also compile it into something that does the right thing in order to pass the test. Finally, a word on the impact of GraphicsFuzz on the Vulkan CTS so far. Over the last year or so, we've added 265 tests to CTS. A bit more than half of them trigger bugs that we found in Vulkan drivers, and then the rest are tests that expose coverage bugs we found using the differential code coverage approach I've told you about. So in summary, GraphicsFuzz finds bugs in shader compilers, and although the tool was developed to work for OpenGL, we're able to find bugs in Vulkan shader compilers by leveraging cross-compilation tools. We've set up a process whereby when we find bugs in Vulkan drivers, we can contribute tests that expose those bugs to the Vulkan Conformance Test Suite. And we've gone beyond bugs to look at using differential coverage and test case reduction to find and fill gaps in the coverage currently achieved by the Vulkan Conformance Test Suite. I mentioned earlier in the presentation that a limitation of cross-compilation is that there's a large part of the surface area of Vulkan shader compilers that we can't hit because of the nature of the code the cross-compiler generates, and our current exciting project is a new tool for doing direct fuzzing at the level of SPIRV, the Vulkan shading language. Thanks for your attention, and I'm looking forward to your questions.